Yeah, so good morning, everyone. And we welcome Professor Deshpande once again for his final lecture on the project which he's talking about. And so let's start. Yeah, welcome, Desh.
Yeah, thanks, Priya and Najam. Good morning to everyone. Today we sort of had a view of Pulsar game in the last two lectures, looking at things from a different point of view than most people do. Today, I'm going to spend time elaborating on the specific lines that I had highlighted in my slides earlier. But before I do that, I would like to attract your attention to several interesting possibilities. We will have, of course, a chance to look at what one can do with archival data, typically on the, the parameters of pulsars, but individual time sequences and their profiles and so on are also available. People have made them available. Traditionally, Pulsar people never shared their data in olden days, but now that has changed positively. In my own kitty, I have a small piece of data that was made available on purpose for students to play with and learn the essential aspects of radio data processing, which takes the voltage data as we call, which is numbers which are proportional to the electric field of the electromagnetic radiation received at any telescope. And this particular data set, without hassles of formatting and so on, has been put in ASCII format, and it's available on the drive. I will certainly share this. I think Priya has the link. She can share that with you, or she might have already done that. So this is basically data on Vela pulsar observed from UT telescope for duration 1 second. So it's not too long, it's not too short. Vela ticks 11 times a second. So you will see about 11 pulses there. And you will get a feel for how to, analyze these things if you have not already done that. There is, of course, a huge amount of pulsar data available for more intense pursuits. So this will give you a sort of a thing to play with and get a feel for issues involved. And of course, much more readily initial processing has been done on these data. They are available at various sites. I have just mentioned some of them. You might find some others describing these data sets and how to get hold of them and so on and so forth. And fortunately, the community has also put together tools to analyze the data that they have made available. So a lot of processing can be achieved by using codes, so you don't have to spend time developing those tools. So I will encourage you to have looks at this and see what appeals to you. As I said, the pulsar parameters themselves, in terms of their location and period and the rate at which they slow down, and lots of things associated with it, their intensity and so on, are available in this famous ATNF catalog, as we call it. It's a pulsar catalog, meticulously maintained, and which has got a, now an interface with a form, and you can ask what, you can seek whatever parameters you want in a table that it will produce eventually when you click a button at the end of it. And you can have that as a data set to begin with for any investigation. There are also useful other locations where you can actually find tutorials on various things where data are made available by the community and what the data represents. Okay. some of them will also give you some, additional general information about the pulsar phenomena itself. Okay, so I will leave it at that, and then I'm now going to scroll through the stuff that you've already seen, and I'm not going to repeat that, except I will stop at places where you will see this mauve color mentions like this, okay, where for example, here I mentioned the end products of supernova explosion. Now, what does that bring up? It brings up possibilities of studying associations of supernova remnants, which are, if they're still around, in the sense they are not disturbed by further happenings in that area. And of course, the way the supernova shell, these are shell remnants, but they may not appear like beautiful shells because of their dependence in evolution on the surrounding medium, density, and so on. So they will expand differently in different directions based on the material that they encounter, and that might lead to or the stuff might have diffused greatly, and so you might find situations where identifying the supernova remnant itself is a challenge, and that can be done by using the property of non-thermal spectrum as against other more circular things that people find often are H2 regions, ionized hydrogen regions. So they can be distinguished, and then you can see if there is an associated pulsar with it, and so on. Sometimes it could be chance, coincidence, superposition. You will have to guard against that, and so on and so forth. So there is a big industry working on supernova and pulsar association, and there is a list of such suspected versus confirmed or more sure associations, and lots of things can be done there, because now you can have a handle on the lifetime of the pulsar in radio phase, which is basically giving you a characteristic age from the ratio of the period to period derivative with a factor of 2, accounting for all this change of rate of change of period. And you will find that that sort of sets the framework in which you can ask when the supernova explosion would have occurred, and it's not likely that the pulsar will be found right at the center of the shell. It might have moved because of its velocity and so on. So there are lots of things that you can do, combining information about the remnant as well as the shell remnant as well as the compact remnant, which is the pulsar. If you see it as a pulsar. Okay. Okay, so I think I had added this, and I probably made this transparency. Okay, so let's go ahead. Now there is there was a statement saying progenitor masses typically greater than about 7 solar masses or less than about 20 solar masses lead to neutron star formation. Now, how do we know that? Particularly the one where the lower limit is assumed, and because of the mass function being such that there are more stars with smaller masses, you will find that it will be dominated by the lower limit of the progenitor mass. They will be the highest contributors, or overwhelmingly major contributors. And so if you they are the ones who will be seen. And there is a study I'm going to mention at the end of this talk, if I find time before 11. It's a case study of how a couple of important things can be inferred by just asking one interesting question. And one of the fallouts of that analysis was getting a limit on the progenitor mass. So this, of course, involved the population study. It involved studying about where they are born and where they have, whether they have the memory of where they were born, and how long it has taken since the formation of the progenitor itself, and how long it takes for them to, explode as supernovae and they have a pulsar left, which we can see. And so that entire story can be built in the galactic framework, and I'm going to describe that at the end of the talk. And this is one of the projects that I would be suggesting, explicit project that some of you interested might want to revisit that study. With remember, this study that I'm referring to was done by some of us when only few hundred pulsars were available. Now there are a few thousand pulsars, and so certainly one can revisit this explicitly, and one will not be affected much by the statistical uncertainties because of small numbers in the pulsar distribution. Okay. Okay, let me come to this. This, of course, a similar study that is possible even now with not a huge lot of more pulsars, but there might be more determinations of polarization position angles, which give you the inclination of the rotation axis. And if more and more velocity measurements, proper motion measurements are done, you will know the direction of the proper motion as well. So one can check how well this hypothesis of producing fast spin and large part space velocity by off-center kick is borne by the data. So it is seen, of course, that this is more true, the velocity and spin axis being perpendicular, particularly for younger pulsars. One can see how does it get destroyed, this particular correspondence for older pulsars, which might have changed their direction of motion because of they are moving in the galactic potential and so on and so forth. So that's an interesting study always, or one should keep an eye on that if there are any anomalies or counter examples of this. Okay. There are lots of studies that can be done. As I said, when pulsars move through a medium where their moving speed is way larger than the local sound speed in that medium, you will see shocked regions and also the material coming out of it through the cones, which give you the particle flow, is also going to do interact with the medium, and we can have beautiful nebulae produced around them. So they can be seen in variety of wavelengths, including in H alpha and at very higher energies, X-rays and so on. So one can look at images and find out whether, so one can actually take the pulsar position and look carefully around it to see whether somebody has missed to note presence of a nebula around it. And then, of course, relating to the pulsar and its geometry, viewing geometry, one can do lots of interesting things. Some examples I had already shown. One learns about more than the pulsar here, about other than the viewing geometry through the nebular emission in X-rays and so on. One learns more about the ambient medium in which things are moving. Okay. About the polarization data, such detailed polarization studies have been done on large number of pulsars, and those data are available at various sites. And this one is looking at these average properties. One has not really fully understood what leads to the circular polarization. There have been compelling explanations, but nothing has been understood to its fullest extent, particularly given that the circular polarization is seen to change sign. Sometimes in in a correlated way with the linear polarization position angle swing. Sometimes there may not be an apparent correlation. So origin of the circular polarization is a very important aspect. People have looked at it. As I said, the S shape itself is a result of this kind of a geometry of our sampling the dipolar field. Now, discrepancies in this or deviations from this expected nice S curve, and there's no one S curve, there are different S curves depending on where you cut them. So this also gives the information about how far you are away from the magnetic pole and what is the inclination of the magnetic axis itself with the rotation axis. So all that information is available, and you would like to do, or sometimes you would like to ask this question, which lots of people have asked, and whether there is a, if you're born with, arbitrary inclination of the magnetic axis with respect to the rotation axis, with time, is there any torque that makes the magnetic axis align with the rotation axis? It's a pretty valid question, and you can visit this and simply ask if the inclinations distribution is sort of more, whatever it is born with, does it evolve, does it change significantly with age? And of course, for that you will require the information on the age, information on the this inclination angle, which is inferred from some of these measurements. And so you can play that game and have your fun investigating these. Okay, there is a lot of stuff to be learned through the viewing parameters themselves, which will help you to account for effects due to a particular inclination situation when you are observing the pulsar. Sometimes you might find it weaker because you might be cutting at the edge of this cone. And also in those situations, you will see the drifting subpulse phenomena more prominently. So you can ask whether there is any, whether we are looking at these pulsars with random cuts that we are not located in any specific position of advantage or disadvantage, and so on and so forth. So some of these things can be verified, whether the impact angle is uniformly distributed, whether the inclinations are any special distribution or the random, and so on and so forth. But in any case, some of this information has to be fed back into knowing the overall luminosity of the pulsar after accounting for the fact that you may not be sampling it at the brightest part, and so on and so forth. All right. Okay. I will come to the cavity. I will not talk about these things separately. The cavity shapes and sizes can be probed through the kind of modeling I showed you for while trying to understand the X-ray nebulosities around pulsars. Vela and Crab were particularly talked about, and so there is a lot to be understood there in terms of the total energetics. What is the radiation pressure overall? Because remember, this is not the radiation pressure in the radio waves that we see. It's the dipole radiation from the pulsar, and also the particle outflow is also going to contribute to the energetics there. So the equilibrium size, which decides the cavity shape and size, can be studied using examples that you might find yourself of, looking at the browsing through the images and something that people have missed, or something that has already been identified by people and talked about but not fully understood. All right. There has been a lot of debate about what is the depth line of pulsars in this particular diagram, for example. The location of this depth line, how is it decided? And we sort of tend to, naively assume that there is some mechanism which for producing large number of particles which can radiate coherently. And then if the mechanism of producing enough potential difference itself halts for some reason, or it's not effective enough, or the potential difference is not large enough, that this entire machinery will stop working. That means the dynamo has become weak. Now, with all that, one can ask whether what this deadline is, what is the threshold potential difference that is required, and you can investigate that quite independently, as people have done, but not agreed upon completely, because there are sometimes when some people had suggested a particular deadline, and there are pulsars seen not a huge lot away from the deadline, but on the right side of the deadline. So, one needs to revise that estimate. And because pulsars should pile up close to the deadline, that is because in this diagram, they move slowly towards, as they go to larger and larger period. That means the rate of change of period is low. You will find the clustering of pulsars here closer to the deadline. So then it's very difficult to find just isolated 1 or 2 pulsars on this side. Why are not they piling up here, and there is a sharp edge of cutoff this threshold? So this is an open question. You can revisit that. What other parameters are not accounted for? It could simply be that the situation is different based on the inclination and so on, whether the corrections for that have been put in. Okay, I think I said this. Regarding the glitches, I'm sure Sushant must have talked more elaborately on this. I myself mentioned one particular example where the glitches or sudden changes in the period, where the slight spin up is seen of the star. Particularly what we see is the crustal behavior. And while they share the angular momenta, you will find the apparent period shortens, and then it recovers or continues. So essentially some stresses are released, and the amount of that relaxation decides when the next glitch will occur. And this has been seen beautifully, not in all examples. So you can revisit this data and see what else has to be accounted for, where after all, it's like the windings that are released, and then how many more windings have to be done before some critical value is reached when the glitch occurs. So that's an interesting thing. For data for these from various observations are tabulated by some people. If they are not on a particular pulsar, you can actually go and visit the literature and pull these things out. Okay, we already talked about this. So of course, as you will see, population studies are very easy to do. You can see in this diagram which population you want to concentrate on, and of course they would have had different life history in their appearance in this diagram. It's less distinguishable in this area, but we in some of our studies had actually seen a signature of this feedback as an additional input to the pulsar population, which you can again revisit. One can actually compute what is called the pulsar current, analogous to the flow of anything, where we can talk of current, which is simply the number times the velocity, right? And you know the velocity along this axis, because that is the rate at which the pulsar is changing its period. So what is called the p dot, the first time derivative of the period, times the number, this defines the current. And one has seen a sudden step in the current at this location, or one has seen a step and one is trying to understand whether it corresponds to a spin-up line, what kind of accretion rate is required for that, and so on and so forth, because different spin-up lines parallel to each other will now correspond to, different accretion rates. So one can revisit that issue. So there are lots of studies, and you can trace back what kind of, as a population, what fraction of pulsars or what fraction of progenitor stars or progenitor systems are leading to different populations. That will also tell you whether how many, you can do some statistical study to see whether the binary survives for the companion to be around still to help the dead pulsar to come back to its life again, its second life. So lots of things are done, can be studied using just this data on the population. Okay, I will not. So what I was talking about is, which one of these scenario is possible? What is the chances or probabilities associated with each one of these? How does it depend on, the system mass as a whole and how much mass is lost? There are things relating to that, very simple principles, which will tell you that this binary will certainly disrupt regardless of any favorable situation of, motion of the companion, how the eccentricity changes, and so on and so forth. So you can use, so most pulsars we believe are born in binaries, and so even that can be tested by estimating the numbers and so on and so forth. So in almost, okay, so let me also visit this. Right. So there could be individual objects, and we can, sort of look at what kind of situation in the past would have led to them being like the way they are now. Pretty much analogous to the arguments put forward by Radhakrishnan and Srinivasan, when the first isolated millisecond pulsar or first millisecond pulsar was seen and it was isolated. There was no hint of any binary companion from its general behavior. But then in terms of its overall appearance itself as a low field short period pulsar, people had inferred this. Okay, I will not talk about this. The different regime of investigation. You can get the timing data and study any binary pulsar in great detail. I'm not sure how much of this data are made available by people routinely, but you can always find some which might be made available. So you can verify for yourself the claims that led to the Nobel Prize, Taylor and Hals, for discovering this pulsar, which led to verification of some of the predictions of Einstein. Okay, like this, for example. All right, if you get data, hold of data which might be more sort of detailed data, where you have the intensity as a function of time and frequency, which is called dynamic spectra. You can do exactly what led to the discovery of the double pulsar. Remember that the double pulsar was detected first or discovered first as a binary pulsar, where the second object, the companion object, was treated as reasonably a similar compact star, like a neutron star. But that it was radiating in radio was not very clear. I mean, it was not known at all. And I think Duncan Lorimer was playing with this data and doing testing some of his software when he discovered another periodicity, and the other pulsar was not radiating continuously. It radiates in only certain phases of the orbit. So it would have been rather difficult to find. So keep in mind that when you browse, when you get a chance to look at this data in the form that is subjected to search for a periodic pulse emission, which will also be dispersed, you might stand a chance of discovering an object that has been missed to be discovered by others. It might have interesting implication, and all that kind of processing and how to see and view and or visualize things can be had by using that pulsar data, Vela pulsar data that I mentioned right in the beginning. It's not a huge amount of data, but it will give you a feel for how things look and what you should be looking for. Okay, and what all can be determined from there. You can also look for situations where you might have intensity data available or some polarization data available on the pulsars, which are in binary, both of them, and so or individual single one when there's the companion is not a pulsar. You can study the effects of spin precession. I mean, you can see the spin precession due to geodetic precession, and so that is, for example, right now, the second pulsar has disappeared from our view because it's not. We are not in its sweep of the cone. When the inclination of the rotation axis there would evolve and change favorably, we might come in its view, and then we might begin to see this pulsar again. So people are actually eagerly looking for this. You might, if some data are available freely after they have done this, you can always revisit that data to see if they have missed. But it can also be studied from, in cases, even isolated pulsar where pre-precision would be there. You can always look at the data taken for these pulsars if it's available over long length of time or over time in terms of the polarization measurements. What does the polarization measurement tell you? It gives you the idea of how the rotation axis and the magnetic axis are inclined. Even if that doesn't change, you will see the rotation axis doing a spin around the mean rotation axis in the precession. And that would change the way we view the pulsar and its intensity and our distance from the magnetic axis. And so that will change the shape of the S curve, okay, as the first causality. And you can actually look at these data on individual pulsars to see how it has evolved over time. Has it evolved over time? And there are people who have made these measurements and made some of the data available, which you might look at. Okay, you know that the pulsar people are hopeful of being able to detect gravitational waves using a set of reliable pulsars, whose ticking rate or the way they tick can be predicted very accurately by having studied their behavior over many decades. People have been using this to see if there is, sign of any gravitational wave having passed through regions where some of the pulsars exist and the direction and so on. There has not been a success, but I think these data are released in big quantities by various collaborations. You might want to look at them, and you might want to play with it yourself if you have some ideas of using them to infer presence or set some limits on the level of gravitational waves. Okay. So this I've been referring to on and off. We have about more than 2,000 pulsars, and we have parameters for about 2,000 pulsars. Not for all pulsars, people might have had the patience to sit and measure their evolution of the period. So period derivative might be missing. If the period derivative estimate is missing, just the period will not give you idea about the characteristic age and the magnetic field strength. But there will be still large number of them where both these measurements are available, and you can have conduct population investigations about other properties and their ages and their distribution as a whole in the plane of period and magnetic field, how things evolve and so on. How they're distributed in the galaxy can also be found out if the dispersion measure is available, and you have a way of using the distribution of free electrons combined with this measurement of dispersion measure, which is nothing but the column density of electrons between you and the pulsar. You can get a rough estimate of the distance and lots of things, even with the uncertainty of distances by a factor of not factor, but at least about 50% uncertainty, you can still get some very important pieces of information. Okay. There is a lot of study that can be done by studying the details in the emission profile, which we said is a signature of the pulsar. These data on the average profiles are available freely from various sites. European Pulsar Network (EPN) made an explicit effort very early on to make these data available readily, and so you can actually visit this and their site and download data. And then if you want to see what is common, uncommon across, what decides the shape, or are there any common threads in the way these profiles appear, you can do that. Similar study have been done by Joanna Rankin predominantly, who studied analyze these profiles in terms of components and has an hypothesis of nested cone structure of the emission region, which leads to based on the cut that you have of this cone, you might get 3-component profile, 2-component profile, or 4-component profile, or more complex profiles, and that is also seen to square well with the way you cut and the way the clues about the way you cut that are available from the polarization positional suite. So you can revisit that, or have independent analysis, or you might even have independent model for this. Okay. Now, the many images and so on available in X-rays these days. You might want to browse through them to see there is a counterpart in X-rays for a given pulsar, and so on and so forth. That is an open investigative trail that you can follow. As I've said here, only young ones are seen to be detected at high energies, so you can see how that corresponds to the actual situation. Earlier, X-ray images were, not readily or available in that kind of coverage of the sky. And now, thanks to many of these missions, you have lots of stuff available to look at. Of course, optical images are also there, and so you can do a combined investigation of that. Okay. You can get these average profiles, get hold of them, which might have been measured at different frequencies. And when you put them together, this is a classic example of two-component profile, how the profile component separation evolves with frequency. And that is tied up with the, so it's in a way a probe of the structure of the magnetic field. People have been believing, and there is enough supporting evidence that that the field well away from the star is largely dipolar, or at least the dipolar component dominates. You can cross-check that for yourself, and evolution of these profiles with frequency also has this additional information about how sometimes you might begin to see other components. Suppose this was the outer shell in the nested cone structure that Joanna has proposed. As you go to lower and lower frequency, you're having a more central cut. The distance between you and the magnetic field is not changing, but the size of the cone, size of the circle, radius of the circle is changing. So effectively, you're cutting the inner parts as you go to lower and lower frequency, and you might begin to see the structure. So you can actually combine all this and even come up with a structure of the cone that might be consistent with this observations. Okay, so that's this is relating to the deadline that I was mentioning, but you can also ask, the kind of electrodynamics that one needs to be operative for everything else to happen, whether that is there, how similar it is for normal and millisecond pulsars. Remember that this potential difference generated depends on the speed at which the pulsar is spinning, as well as the magnetic field strength. You know that the magnetic field strengths of millisecond pulsars and normal pulsars are, they differ by orders of magnitude, almost 4 orders of magnitude. And so there is a large significant difference in the spin periods. So you can ask it so happens that the peculiar combination of the period and magnetic field leads to roughly similar potential difference that can be produced. So the dynamo are equally effective in both cases. So you can see that or see any deviations from it. What is happening inside the polar gap is something where if there are sparks and certain locations where the potential difference drops momentarily because of the flow of a current, like in a capacitor, you will find that leads to this structure which has got this discrete spots, and you can if there is rotation of the system, you will see drifting subpulses, which you can study. So let me go back. Okay, where was I? All right. So you can study the behavior in this 50 meters of this polar cap region. You can also study, we say that radio emission is a tiny fraction of the rotational energy loss. The rotational energy loss is largely through the dipole radiation. We can estimate the amount of dipole radiation if we know the period and the period derivative, assuming that the energy loss is due to, or regardless of what the model is for loss of energy, we can have we can actually get an estimate of the energy loss directly if we just assume the moment of inertia. And radio emission is seen directly. You can make an estimate based on any spectral behavior that you can infer from measurements at multiple frequencies, and see that entire radiation in the radio range can be estimated. And you can ask what fraction it is of the rotational energy loss. This has not been done very systematically, okay? But whenever studies of luminosity of the pulsar are done, radioluminosity, of course, one has used this information about the radio intensity and try to see its behavior. There is a lot of scatter in the way that when you try to probe its dependence on the magnetic field and period by asking if it's the same fraction of the rotational energy loss. And there have been other models proposed where different trends are seen, different dependencies are seen on the period and magnetic field strength. So all that is can be revisited. Nothing is stated with any confidence there. But we use some best fit models to progress when we want to know what the typical radio emission will be, and so on and so forth, if there is certain distribution of things in period and magnetic field. The signatures of coherent amplification, of course, the key details are missing, and all studies of pulsar emission would lead to eventually the getting closer to learning about how the coherent amplification takes place. And the studies related to that are the important clues, of course, come from the differing subpulses. So many, for many pulsars, the pulsar time sequences are available, and you can study these things by analyzing them in their fluctuations. You can also study nulling, which Sushana has already elaborated on, so I'm not going to spend much time. How the profile changes occur, what are the time scales, do they depend on the pulsar parameters that are readily available, or there's some hidden combination of it, or other parameters, situations that influence this, that is not known. You will have ample data to study that. I already mentioned about the position angle, polarization position angle. One also has seen that jumping by 90 degrees without warning, or sometimes very systematically in certain locations of the phase. Why that happens is not really known. One believes that there are always two orthogonal modes which are superposed, and the relative intensities associated with that will decide what the net polarization will be. And remember, there's incoherent superposition of it. That means you're not going to get changes in the position angle due to this superposition. You will just get one of them dominating. There is also, if you go get hold of data which is raw voltages like the one that I mentioned in the case of Vela, you can also analyze this at the highest possible time resolution and study the microstructure, which otherwise gets washed out in the normal processing of pulsar data. You can also look for giant pulses. You can do the statistics on them and see what clues you might get about the production of the giant pulses. Okay. Of course, the classic case of part-time pulsar is a very unique case, but you will find very similar cases available in the if you dig enough in the literature or hunt around for data, you will find then you can study its slowdown, the overall slowdown rate, and when it was bright, what was the slowing down, if you have enough data, and you might find similar part-time pulsars. Of course, it is when they are off, and if one was doing any search observation, you're not going to find them. But you could be lucky, in addition to the scintillation enhancing the intensity once in a while, you will be lucky that it might actually be in the active phase of the such part-time pulsars. Okay. As I said, you can study the drift, the drifting subpulse behavior. You can estimate the circulation time, the time it might take for it to go around. Although you might see the behavior only here, so you have to hypothesize between what this angle is and how much time it took to cross this, and then scale it to the 2 pi track. When you do that, you can check out how it squares with the prediction and the reasons for this behavior in the first place. And you might get enough data on this enough pulsars. Such data might be available if you look carefully, and you can begin to ask this question: that is, this model of E cross B drift is able to explain this? And if it does it require any specific radius along with at which these sparks are preferentially generated, and so on. Okay. You can, of course, these are detailed observations, and they can always be viewed in fashions that are shown here, but that just produces beautiful views. Much of the information can be extracted without making such views. All right, I already mentioned about pulsar wind nebulae and the supernova shell, and it's for example, here the pulsar seems to be moving in this direction, and if you trace it back to the lifetime of the pulsar, back to its sort of roughly around its birthplace, it will be seen there. Now that is not consistent with it's being born at the center of this, and so there are questions and puzzles that are still to be solved, and it might make us wiser in terms of what actually happens, what besides the location of the pulsar that we will see today, and how does the shell remnant also evolve. So, for example, it could square well with if the shell is anyway seen only partly, and the shell might actually have a center there. So things like that. Okay, you can also ask whether pulsars have memory of where they were born, whether if large number of pulsars, in fact, majority of the normal pulsars are probably born in the galactic plane, in spiral arms, or in associations of massive stars, O and B associations. You will find that if there is enough information available on their velocity, you can trace that backwards to see if they came from same parental or neighborhood, even if they are seen today in different places because they got kicked in different directions and so on. So there are lots of interesting questions that will be asked. X-ray nebulae, of course, would be seen. What I want to say here is this beautiful image of X-ray nebula was not produced because one wanted to study the nebula, and that was the target, declared target. One actually was studying some glitch phenomena in the case of Vela pulsar, and wanted to see at the time of the glitch whether there were any appreciable changes in the X-ray intensity of the pulsar. And when they were doing this observation, of course, the image came free in terms of even the abilities of this. And so there are lots of images that might have been made while observing some object for some other purpose, and your eyes might pick up things with such morphology, and then might have corresponding study undertaken. Okay, there's nothing here extra to add. I think we've gone through this, so I'm going to basically stop here. And so evidence of free precession can come from polarization studies and so on and so forth. Okay, I'm going to pick up on this case study very briefly. I will, so interested people can get in touch with me to repeat this. This is some work we did in '95. The question was asked very simply that we have pulsars born in galactic plane, or at least the progenitors of pulsars, which are massive stars within the range of 7 to 20 solar masses, are born in the galactic plane or galactic disk, at very low latitudes where the massive stars are, and they evolve as normal stars, give rise to supernova explosions if they are massive enough, and might lead to birth of a pulsar. Pulsar gets a kick and it might migrate from that place, and all that might happen. So the question was, by looking at the present locations of the pulsars, do they have a memory which is not erased by their random motions that come up subsequently, that tells you about when the progenitor stars were born. The progenitor stars were born at some time and in locations preferentially of high density, which is tied up with the spiral wave pattern, okay, at that time. Then they're born as massive stars. Then they might take certain time to evolve. How long they take depends on their mass. And so by then, what would have happened is the spiral pattern would have moved. And today's spiral pattern is not going to be what was seen a million years ago. And by knowing the correlation or investigating the correlation of distribution of pulsars today, which have not spent much time in comparison with the evolution time of the star, which led to the pulsar, they would be still around, roughly around the same place as where the explosion took place. We can ask where these objects are seen today and where they would have been N years ago if we knew the gap. So we can ask for correlation of the spiral pattern, and assuming that there is differential rotation of matter. Okay, both these things put together, we can ask whether the present distribution of pulsars squares well with them being born in the spiral arms some tens of million years ago. This gives you a handle on variety of things. It tells you about how the pattern is rotating, if you do find such a correlation. It tells you, and that's one of the very important parameters for the galaxy. It also tells you the gap in time, and you can account for part of it for the lifetime as pulsar, and the rest of it is evolution of the star, which is a progenitor of pulsar. And this is how, by knowing that time difference between or the duration, the lifetime of the progenitor before it became pulsar, that one has inferred this lower limit of 7 solar masses and so on. There are other ways, of course, estimating this. So these two numbers can be inferred importantly, and then you can see that this investigations can be done. So if people are interested in revisiting this, as I said, this investigation was done almost 25 years ago, and one didn't have as many objects to investigate this properly. You can revisit this with now 2000 pulsars, or more than 2000 pulsars. So if anybody is interested, they can contact me and we can continue this discussion offline. All right, thank you for listening.
Yeah, thanks so much, Desh. We already have a question in the chat window. I know you are in a hurry to go, but
no, that's fine. But I will answer the questions. Then
I think you can read it, or should I read it out to you in the chat window?
Pardon?
In the chat window, can you read it, or should I read it out to you? There's a question.
I've just brought it up and I'm reading it.
Yeah.
So, all right. Okay, as we know, Black Widow, Red Back are binary millisecond radio pulsars. My question is, in this reference, is what makes their pulsar winds to destroy their companion? I think the pulsar wind is actually a very powerful source of, the energetics associated with that is almost comparable, as we have seen from the part-time pulsar, comparable to the sort of energetics in the magnetic dipole radiation. So I think it's just the, in what stage the companion is, right? That will decide after it has spun it up, the job is done, and it's still evolving. You can basically see the pulsar wind is strong enough, the momentum and the energetics is high enough that it can blow the loose material away and really, strip the companion of its matter.
Yeah, thanks. So, do we have any more questions?
Okay, there is a raised hand apparently. Suman, yeah.
Yeah, Suman, you can ask. If you want, you can unmute also.
Yeah, hello Desh. I want to ask that is there any archival data source for studying pulsar planetary system, and what is the current interest to study pulsar planetary system?
Yeah, so there is tons of data available on individual pulsars on their timing. Okay, now this entire set of inferences about them having companion and what the companion mass is and so on, whether it's in a planetary range or a normal stellar range, all that is inferred from the behavior of the arrival times of this pulsar, arrival time of the pulses seen in this pulsar, and such data are made available after calibration and so on. Okay, this is the same collaboration that has made this is trying to detect gravitational waves. So if you have patience and interest, you can always download this data and try to fit a model for behavior which which might be just simple evolution versus if it's already known to be in binary, you can fit that model, and then you might see the goodness of fit. And sometimes you might find discrepancies, anomalies which stand out in that fit, which is what would lead you to invoke another object which can explain the behavior, which might have modulated the arrival times of the pulsar, radio pulsar. So yes, the simple answer to your question is yes, these data are available, put forward by this international collaborations for pulsar timing arrays. Now, whether there is enough interest in the in this aspect. Of course, there is continued interest. I think the general masses are pretty happy to support activities which will lead to any investigation about life elsewhere and so on. So you will never have dearth of funding for such things. Does that answer your question, Suman?
Yes. So basically, the binary pulsar and pulsar planetary, you are saying that the study is same for both binary pulsar and pulsar planetary system.
Yeah,
The
because
way
it
of
is
study.
binary is just first step to the planetary system. If you just had a star and a planet, okay, a single planet, you would see it as a binary, and you will see perturbation in the systematic cyclic, periodic perturbations in the arrival times, which you will try to understand in terms of having some body going around it, and the pulsar effectively going around its the center of mass of the system and all that. So this is how you detect presence of another body, and planet is just a special case of it, because the masses of these bodies happen to be in certain range, and a system is simply a single object, single companion is not able to explain. So you try to model it as combined behavior of more than one object, and so on and so forth. But it's all the clues come from the timing measurements.
Okay. Yeah.
Desh, I don't want to hold you long because you have an important meeting to attend.
Okay.
So
we can, yeah, if required, I'm happy to come for a brief session, special session for any pending questions that people might have. If they want to discuss them together rather than individually, it will be difficult to answer. But people interested in the sort of project that I mentioned can get in touch with me or contact Priya, and we can coordinate that later.
So actually, tomorrow we'll be winding up with all the lecture series, and then we'll try to formulate groups of people who are working on common projects.
So I might tune in tomorrow.
Yeah.
Okay.
Yeah. Sure.
And then we can take it from there. Okay.
Yeah. You can come into the same link, and that's
okay. Wonderful. Okay. Thanks a lot, everyone.
Thanks a lot. Thank you so much.
Sorry, I need to rush. Yeah.
Yeah. No problem.
Thanks, Desh. Thank you.
Okay. Yeah. Thank you, and bye.
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 So we'll end today's session with this thing, and like we mentioned, tomorrow we'll have the final session. Okay, and after that we hope to formulate groups of people. So December and part of January would be used on doing your projects, and then what we have decided is that the end of Jan, I mean, at the second half of Jan, students can actually, or participants can actually present their projects, and that would be in the second half of January. So you'll get 1.5 months to work, and it can be done as you wish. If you want, we can coordinate your meetings with the mentors, or we'll have the groups, and groups can do it like that, right? So tomorrow I will already put up a Google form where we will categorize you all into whatever projects you all opt for. And then people working in the same project can link to each other and work accordingly, right? So we'll end today. And you want to say something? Yeah. And we'll meet tomorrow morning at 10 o'clock. Yeah? Yeah. And if there's anything you would like us to do tomorrow, please mention it, write it on email or Telegram or however you wish, and we'll cover those things tomorrow. Because otherwise, tentatively, we are planning to finish with these lecture series tomorrow, so that then you all can work for the remaining time, right? So see.